Good afternoon. Thanks for joining me here today. My name is Graeme Keith. I'm an independent consultant advising on mathematical modelling for strategy and risk management. You can read about me on the Risk Awareness Week webpage and on my LinkedIn profile, so I won't go on about myself now. We'll get straight into the material. Suppose I have a series of binary events, things that either happen or they don't. I have at some point in the past made assessments of the probability of these events, and I now know the outcomes of all of them. Maybe I had a set of risks and I assessed the probability of those risks happening in the course of the year. If I was modelling credit risk, I might have a list of debtors with a probability of default in the course of the year. It might be a list of oil exploration wells with a probability of finding oil, or maybe I'm calibrating my probability skills and I just answered a series of questions together with the probability that my given answer was correct. Wherever it came from, whatever it is, I'm now sitting here with a list of probabilities and a list of corresponding outcomes. This is what it looks like. So this is my list. I have 50 here. My goal now is to try to answer the very reasonable question, were these assessments of probability correct? But this leads me straight into the question, what is a correct probability? Is there even such a thing as an objectively correct probability? To give a sense of the problem, say I assess the probability that an oil exploration well discovers oil at 20%. We drill the well, we find oil. Was that assessment correct? After all, I said it was much more likely than not that I wouldn't find anything. So was that assessment correct? Now, frequentists believe in an objectively correct probability. But their only access to objectively correct probability is through frequencies in large numbers of repeated identical experiments. So they things like, if you drill that well 10,000 times, then the average number of times you discover oil is the correct probability. The problem is we all know full well that if we drill that well 10,000 times, we're either going to find oil 10,000 times or we're not going to find it at all. There's no repeated experiment here. There are metaphysical workarounds, but there's something very unsatisfactory about an utterly inaccessible notion of probability and an inability to say anything interesting about a set of assessments other than the probability that they are or are not absolutely correct. So that'll bring us to Bayesianism. Now there's a school of Bayesianism, which is quite popular, that talks about subjective degrees of belief. So they don't believe that there's an objectively correct probability. I like Bayesianism, but I find this quite upsetting. It's a terrible license for all sorts of nonsense. What I'm going to do in this talk is to try to adopt a pragmatic approach, and I'm going to argue that that pragmatic approach brings us to a notion of objective probability in a Bayesian context. What do I mean by pragmatism? What do I mean by pragmatic? I'm talking about pragmatism, the philosophical tradition that started in the late 19th century and continues to this day, but it will turn out that the pragmatist approach is also pragmatic in the everyday sense of the word and terribly useful. The essence of the pragmatic school of philosophy is summed up beautifully in this quote from Charles Peirce. This is Peirce. This is Peirce when he graduated Harvard, before he got his pragmatic beard. All old pragmatists have beards. What Peirce is saying in this quote is saying, don't get too hung up on what objective probability is. Don't worry about trying to define it. Think about how you're going to use it. And what he says is consider the practical effects of the objects of your conception, in that case, objective probability. Your conception of effects, of those effects, the practical effects, is your conception of the object. So he's saying we define the things that we're interested in by how we use them. So think straight away about if you had something called an objective probability, how would you use it? Okay, the problem with my 20% recovery well is that the outcome is too uncertain. 20%, 4 to 1. It's not great odds, but it's still more likely than getting out of jail in Monopoly. So even if the 20% is objectively correct, I can't really say anything useful about it on the basis of one outcome. To be able to say something a bit more practical, I need to be able to reduce this uncertainty. But I have a list of probabilities. So I can do things like looking at the total number of events that happened. So the number of risks that occurred, the number of debtors that defaulted, the number of discoveries made, the number of correct answers in my calibration list. By looking at the total, that will reduce the uncertainty a bit. Now with the notion of correct probability, I can ask myself, if my probabilities were all correct, what would be the probability distribution for the total number of occurrences in that series of events? Now, this is useful because it tells you things like how many events you'd need in order to say anything meaningful about how good the constituent probabilities are. Now, the easiest way to calculate this aggregated probability distribution is to download the free version of Model Risk from Vo software and run a Monte Carlo simulation. But if it's a short list, you can do it by hand. And if it's a long list, you can use the central limit theorem and approximation. Either way, you get something that looks like this. So on the horizontal axis here, we have the different numbers of outcomes: disasters, defaults, discoveries. And vertically, we have the probability of getting that number. The bars here are a direct calculation, just calculated from that list of probabilities, and they're all different, those probabilities. The curve, which you can hardly see is a curve, it just looks like an envelope around the bars, but that is actually a curve that's approximating those bars pretty damn well. Fine. That's the probability distribution over the number of occurrences. So far, so frequentist. The question is, are we that much wiser? This is the actual number of outcomes. So I have my list of probabilities, and then I've added up all the things that happened, all the risks that took place, or all the discoveries that were made, or whatever. And I came in low. Obviously, that's good if we're looking at disasters, and not so good if we're looking at discoveries. What we can't really see here, when we've just come in low, is, was this bad judgment or just bad luck? Luckily, there are many more practical things that we can get out of this notion of objectively true probability. Let's say there's such a thing as an objectively correct probability, but for whatever reason, congenital optimism, human heuristics, bias, mathematical ineptitude, I consistently and systematically get it wrong. Now, interestingly, it's only the systematic biases that we can hope to capture in this kind of analysis. Random errors, just going a bit high here, a bit low there, or errors that are unique either way to the individual things that we're looking at, those things will tend to cancel out in the aggregation that we do to reduce the uncertainty. This is the price we pay for aggregation. We reduce uncertainty, but we give up being able to say anything about individual assessments. But we're interested in systematic bias because if we're doing a look back, we're doing it in order to be able to find the systematic problems that we can fix. It turns out very usefully that because of the way that random variables add up, the way they behave when you add up, there are only 4 kinds of systematic bias that we can hope to catch in this kind of analysis. These are the 4 biases of the apocalypse. Optimism, pessimism, fairly straightforward. It's just pitching the probabilities too high or pitching them too low. Polarization is when the correct probability, the objectively correct probability, should be a little bit higher than average, but you take it and you jack it up very high, or if it's a little bit lower than average, you take it and you push it right down into the doldrums. So it's this sort of idea of it's good, it's very, very good, and if it's bad, it's horrid. It's a reflection of overconfidence in your ability to assess data, or it's because you're reading too much into the data. Geologists are absolutely terrible at this. The converse of polarization is vagueness, and that's where you never get off the fence. So if the probability is less than neutrality, then you tend to push it back towards some sort of neutral baseline. If it's above that neutral baseline, you tend to pull it back again. And it's hedge sitting. You're just fence sitting, rather. You're just sitting on the hedge the whole time, the fence. We see this, it's rarer, you do see it, sometimes because of an overcorrection to polarization, but sometimes also because people are gaming their probabilities in order to get good results on average. So this is all well and good, and there's a lot of sort of mathematical argument behind this, but I'm a numbers kind of a guy, so I want to quantify these biases in some way. It's not just enough for me to say, yeah, optimistic, pessimistic, polarized or vague. I want to be able to put some numbers on those things so I can make comparisons. Now, if you're the kind of person, if you're this guy whose head explodes when the formulas come up on the blackboard, then please bear with me for one slide. The next slide is the mathematical detail, and it's in there for people who speak math. You shouldn't need it in order to be able to understand what comes afterwards, but obviously you'll get a slightly richer idea if you do speak math, if you follow me through this slide. So if this is all gobbledygook, then please just ignore it and join me again on the other side. Okay. How to model bias in one slide. The challenge with modeling bias is that you can't just add probability to probability. So you can't just say, okay, I'm over-egging my probabilities by 20% each time. It doesn't make sense. It doesn't make sense for two reasons. Firstly, if you start with a probability of 90% and then you raise it by 20%, you end up with a probability of 110%, which is unsettling. But the other problem is that if you have a very low probability or a very high probability, it's because you have a lot of evidence that it's never going to happen or it's absolutely going to happen. And then a little bit more evidence shouldn't be pushing you that much either way. So the bias shouldn't make that much of a difference in very low and very high probabilities, but it should make a lot of difference in the middle where your information is indifferent. And that's what we're going to try and do. That's how we're going to model the bias. We're going to mimic the process that probabilities are biased, and we're going to use that using Bayes' theory. Now, Bayes' theory is marvelous, and it's marvelous for telling you how to modify probabilities in the light of real information. What we're going to do is we're going to say that biases are essentially false information, and we're going to model how the probabilities change accordingly. The problem is that Bayes' theory is really ugly, and it's ugly, I mean, it's ugly, but it's ugly because this thing here, which is the probability of the thing that you're modifying, your prior probability, the probability that you start with, the unbiased probability, crops up all over the place, and it makes it very awkward to work with. So what we do is a little bit of mathematical magic, and we switch over to something called evidence or log odds. And the way you make the evidence is you just take the probability, divide by the probability of it not happening, take a log and multiply by 10. The 10 just makes the numbers nice. It's not important. Now, this evidence is just another way of writing probability. If you give me a probability, I can tell you what the corresponding evidence is. And if you give me an evidence, I can tell you what the probability is. This graph here shows how this is probability on the horizontal axis and evidence on the vertical axis. If you give me a probability, I can read off the evidence. If you give me an evidence, I can read off the probability. You can see probability goes from 0 to 1, as we all know. Evidence goes from negative infinity to positive infinity. And that's one of the reasons it's actually very useful. Now, it's a bit of a headache to switch backwards and forwards between probability and evidence. The reason we do it, the reason we pay that price, is that Bayes' theorem, when expressed in terms of evidence, is an absolute pearl of an equation. It's a beauty. So here we have the evidence. This is sort of probability in this direction, given a piece of information. And when I'm modeling bias, this is a spurious piece of information. And what it says is that that is just the evidence without that spurious piece of information plus a number. That number depends on how likely you are to see that information in the positive case versus how likely you are to see it in the negative case. Now, this is spurious information, so we just add in a number here, and that mimics optimism. So we're just saying that optimism is like having spurious positive information. Pessimism is like having spurious negative information. These are these transformations out here. And then polarization is when we take a probability that's above 0 and we move it further away, and we take a probability that's below 0 and we bring it down again. So what we're doing there is just multiplying the probability in evidence space, and that's pushing it further away from this neutral point. And likewise, vagueness is just dividing, is just bringing it back or multiplying by a number less than 1. So very simple linear transformations in this evidence space mimics the biases that we need to model in order to be able to capture bias. What I end up doing is I end up putting them together. We can compound these transformations, and we can capture all of the 4 biases in one simple equation with 2 parameters. Those 2 parameters capture optimism and pessimism, that's the A here, and polarization and vagueness, that's the B here. So that's a very nice model. Now, if you switched off at that point, this was all gobbledygook, come back to me now, because I'm going to try and explain what this means in terms of what it does to probability. So what I've done here is I have this model that has 2 numbers, one for optimism, pessimism, one for polarization, vagueness. And according to what those numbers are, I move my objectively true probabilities into a sort of distorted bias probability. So in this case, I'm plotting the objective probability here and the bias probability here. Now, if there's no bias, there'd just be a straight line here. But in this case, I have mild optimism. And what it's doing is it's lifting the probabilities up, but it has that feature that's lifting them more up in the middle than it is at the ends. This is a slightly wilder optimism. I'm still very much within the bounds of what we see when we do this analysis, and it's moving the probability quite substantially through here. This is pessimism, obviously the same sort of thing, but the probabilities are now coming down. We have polarization, that's this thing here. And as I say, if you go slightly above zero and you're polarizing, things that should be a little bit above the neutral point, they get shifted up, and things that would be a little bit below the neutral point, they get shifted down. And mild vagueness, this is the situation where if you have a probability that should be negative, it gets pushed back towards the middle, and things that should be positive get pushed back towards the middle. Now, this is pure optimism, pessimism. This is pure polarization, vagueness. But we can mess these things up. We can mesh them together, and we can extract optimism, pessimism, polarization, and vagueness in one single transformation. So what? I have this conception of objective correct probabilities, and I have this really nice model for creating bias. How do I put these things together to get something useful that also explains what we might mean by objective probability? What the concept of an objective probability does for us is it allows us to tie the outcomes back to something well-defined, i.e. the probabilities that, statistically speaking, would give us the outcome. Now, obviously, we can't know what these are exactly point for point, but what allowing them to be a thing has done is it has allowed us to set up what is essentially a regression problem to work out the bias parameters, those two numbers that describe all the possible forms of bias. And that's what we're after. I'll show you how this works in practice. What I do, I start with my list of biased assessments here and the outcomes. I take the biased assessment and I wash them backwards through my systematic bias model. So essentially what I do is I lay the biased assessments up on the axis here, and then I read off what the true probabilities should have been for some choice of the parameters A and B here. Now I go back to the objective probabilities, and then what I can do is I can say, okay, let's look at what these objective probabilities predict, statistically speaking, relative to what we see, the list of outcomes here. And what we can do is we can just move A and B around until we get a good match between the objective probabilities and the outcomes. And there's essentially two ways of doing that. We can do a simple regression analysis, just looking just to minimize the error. So what I'm plotting here is along this axis, I'm plotting the pessimism optimism number. That's A in the formula, if you remember that. So down here, I'm pessimistic putting the probabilities down. Up here, I'm optimistic pushing the probabilities up. And this is vagueness and polarization. So down here, I'm pulling it back to the middle, and up here, I'm pushing it away from the middle. And this is the error function. So this is the extent to which the probabilities, the predicted correct probabilities, match the outcomes. And what I can see is that they match best when I've been slightly optimistic and actually fairly polarized. So that's the conclusion here. This is really just telling me one answer. This contour plot doesn't really mean anything other than it tells you where the minimum is. A much better way of doing this, I think, is to do a Bayesian inversion. And what we do there, essentially what we're saying there is we're calculating what's called a likelihood function. So what we're doing is we're saying, okay, what's the probability of seeing the outcomes that we see for a given choice of these two bias parameters, A and B? So again, this is the pessimistic or optimistic bias parameter. This is the vague polarized bias parameter. And what I've done is I've just plotted the probability of seeing the probability of the data that we've observed as a function of those two parameters. And again, what I see is that the most likely combination of parameters relative to the data that we see are one which is slightly optimistic and slightly less polarized than here, but they're pretty close to each other. The beauty of this is that this thing is an uncertainty distribution. Now, if we're working in a Bayesian context and we had a prior, this is the thing that we would update the prior with. If we didn't have a prior, we might have some sort of flat uniform distribution. This would be the sort of first guess of what the distribution would look like. So essentially it's sort of applying it to a uniform prior, but there's some technical details with that, why that's a bit awkward. But the point is that this shape, this contour shape here, actually mimics the uncertainty in being able to set that parameter. Now that's great, because not only does it tell you whether or not you're being optimistic or pessimistic, polarized or vague, it also tells you the certainty with which you can make that conclusion. So if you have only a very few data, this will be a big hill all over the place. It'll be splattered out, and you won't be able to conclude anything very conclusive. If, on the other hand, you have lots and lots of data, it would be much narrower. It also captures whether your bias is systematic. If you don't have a systematic bias, this will be much more spread out. So if you're just random, then again, this would be spread out. If you are not random and you don't have a systematic bias, it'll be peaked in the middle. It captures all of those behavior. So what have we done? We've allowed for the existence of objective probabilities. We've taken this pragmatic approach and decided just to use them and see what we could do with them if we had them. The first thing we did was recognize that there were only 4 systematic biases that we could hope to extract from a look-back analysis. And then we came up with this forward model using Bayes' theory for them. That allowed us to do this inversion, this regression back to the bias parameters. So this approach is about assuming objective probabilities and then finding what the bias has been that has generated the sequence of probabilities that you actually have in your hand. Now, it's an incredibly efficient method because it focuses all the data on what can be found. It doesn't waste time with this random stuff that can't be found. So it's saying all there is these parameters, so these 2 parameters. So we're going to focus all the data on that. So it's very efficient. You can get a lot out of a relatively small number of data points as long as the bias is actually systematic. It's also a very honest method in the sense that if there aren't enough data to say anything very clearly, or if the assessments are all over the place, then you're left with this big range of uncertainty on the parameters, and you can see that in the Bayesian update model. It's also a method that allows you to make comparisons between all sorts of different situations. So we can compare companies doing the same sort of thing. I've done a lot of work with this on exploration companies trying to assess the probability of finding oil, and I'm beginning to see where on this graph different companies are falling in. So companies that are very optimistic, they sort of fall over here. If they're polarized and optimistic, they'll sit here. So I know where these things are. Now, obviously, it's anonymous. I can't share that with people. But what it means is that once you build up that experience, you can see, if you do an analysis for another company, I can see, how do you lie relative to the sort of performance in the industry? And that's something that's very, very difficult to do with traditional look-back methods. So there's a lot of practical benefit in this methodology. But for me, fallen philosopher that I am, what I really like about this whole approach is that it provides a notion of objective probability in a Bayesian context. Now, I can't abide for quintism. It makes no epistemological sense to me at all. But the notion of subjective probability is also very upsetting. This approach puts the objectivity, that is the big hallmark of frequentism, into Bayesianism. And that gives me a lot of comfort at night. Thanks very much for your attention.